A major goal in analysis is learning how to replace messy, complicated continuous curves with simple, predictable polynomials. This journey eventually leads us to the Weierstrass approximation theorem, but getting there requires us to carefully define what it means for a sequence of functions to reach a limit. We start with a baseline mechanism, pointwise convergence. This means picking a specific point on the x-axis, tracking the sequence of functions along that vertical line, and watching those individual values drop down to converge at a final coordinate. If every function in our sequence is a smooth, unbroken line, it feels intuitive that the final curve should also be unbroken. But intuition is fragile in analysis. Walter Rudin formalizes the danger here, labeling it the main problem. Can we take a limit of a limit and safely swap the order in which we calculate them without altering the final mathematical outcome? Assuming these limit operations can be casually interchanged is a trap. If the order of operations changes the result, the foundational rules of calculus start to break apart. Look at the discrete double limit in example 7.2. If we evaluate the limit as m approaches infinity first, the math resolves to 1. But if n approaches infinity first, the result is exactly 0. The order completely dictates the answer. This instability infects continuous functions as well. Example 7.3 sets up a geometric series based on an active x variable. As we add more terms, the arms of the curve pull down toward the origin, flattening perfectly. But at x equals 0, the sum resolves to 1. The sequence snaps, leaving an isolated, disconnected point on the y-axis. Apply this logic to the factorial cosine function in example 7.4. If x is a rational number, the sequence eventually locks into an integer multiple of 2 pi, evaluating to 1. But if x is irrational, the term collapses to 0. We are left with a limit function but violently jumps between 0 and 1 at every single coordinate. Pointwise convergence has taken a sequence of perfectly smooth inputs and shattered them into a disjointed, ungraphable result. Continuity is lost. The damage extends to standard calculus operations. Example 7.5 gives us a sequence of sine waves that progressively compress, converging point by point to a flat horizontal line at 0. You would naturally expect the final derivative, the slope, to be 0 everywhere. But watch what happens taking the derivative before the limit. As the sine waves squash down, their frequency spikes. The slopes become violently steeper, and at x equals 0, the derivative shoots straight up to infinity, contradicting the flat limit function. Integrals fail just as dramatically. In example 7.6, the sequence creates a geometric spike. As the sequence progresses to infinity, the base of the spike gets infinitely thin and slides left toward the y-axis. The limit function drops to 0, implying 0 area. Yet the peak of the spike stretches astronomically high, trapping a solid block of mathematical area that refuses to disappear. Slopes escaping to infinity and trapped areas surviving a flat limit prove that pointwise convergence cannot be trusted to preserve the rules of calculus. A much stricter mathematical framework is now required. This brings us to definition 7.7, uniform convergence. This is the stronger rule required to safely interchange limit operations. Think of epsilon as a rigid, uniform tube wrapped around the final limit curve. For a sequence to converge uniformly, the entire function curve must slide inside this tight boundary at the exact same time across all possible values of x. Look back at our trapped spike attempting to grow. Under uniform convergence, it violently collides with the top of the epsilon tube. The strict boundary forces the entire shape to comply, explicitly prohibiting the infinite slopes and delayed snapping points we witnessed earlier. The main problem is solved. By demanding that a sequence fits within this boundary everywhere simultaneously, we guarantee that continuity, derivatives, and integrals are safely preserved through the limit process. With the mathematical safety of uniform convergence established, we finally have the bedrock required to prove that complex, continuous curves can be reliably and precisely mapped by simple polynomials.